Linking and loading, linking. We're going to go through the linking and loading process, and in this part we're going to go through the first part, which is linking. So what is linking? Let's take a look at a sample program to understand what's going on. So here we have two different files. So we have main.c and sum.c. We want to be able to compile a program in these two different files and then combine them into one large overall program execution. So in this file, we have an array that's being referenced. It's referenced here. We're declaring here a routine sum that exists in the other file. And we need to know what the arguments are for C to be able to pass the correct argument types to it. And then we declare the main function. Overall, in the second file, we actually declare the body of the sum function that was the declaration of which was declared in the first. When we combine or compile both of these files, we can combine them. We can either do it on one GCC command line. So here we're saying compile both main.c and sum.c, and then I want to produce a file named program out of that. So each of the files is then individually compiled. So the main.c runs through the compilation process, sum runs through the compilation process. We're left with object files, .o files that then contain the binary portions of the files plus what are called relocation information and symbol tables. The linker then combines the two different .o files, the object files, to a single program, the program file. So why do we have linkers? More or less what I just said. Why do we have linkers? The first reason, modularity. So then we can write programs in smaller parts and combine them together instead of having one monolithic mass program. This was an innovation as programs got larger, and it also has been used for being able to separate out programs and have different people work on subparts of a program. You can then also build program libraries that have common functions. So instead of having your own version of printf in your single C file, you can use the libc version of printf. The other reason we have linkers are for efficiency. So we can separately compile programs. The individual main.c and sum.c can be compiled, and then if we just change one of them, we just need to compile that one file and then relink things. And the relinking process is typically much, much faster than compiling. Although you might think that separate compilation is not a big deal because, I mean, how long does it really take? However, for example, if you're compiling large programs, let's say the Linux kernel, which has thousands of files in it, it can be a several hour process. And so having a separate compilation mechanism is really useful if you're then in a development cycle. Even for other applications, having that separate compilation really helps the edit debug cycle. The other thing that linkers give us is space efficiency as well. So common files can be aggregated into a single file, and yet the executable files and the running memory images contain only code for the functions that they use. We're going to see that this is a big advantage of what are called shared library files, or DLLs in the vernacular. So in these cases, a shared library file will be shared across multiple programs running concurrently, and a single instance of that library will be taking up RAM in the physical computer system. So what do linkers do? The first thing that they do is symbol resolution. So a program has a set of symbols, which are global variables and functions. So for example, swap is a symbol. This is the definition of a symbol as we define the function. It's the definition because we're providing the body of the function here. This is then a reference to the swap function. We're actually trying to be able to use it. This is both a definition of a function of a symbol, the xp, and a reference to the variable x. Symbol definitions are stored in the object file, and they're placed there by the assembler in something called the symbol table. The symbol table is an array of structs of organized data about the individual symbols in the symbol table. So they include things such as the name, the size, and the location of the symbol. The name is pretty obvious, so for example, for swap, we would include swap. What's the size? It's how many bytes this code is. And the location would be both the location where it is in the object file and then later on the location in the executable. During the symbol resolution step, the linker associates each symbol reference with exactly one symbol definition. So in other words, there can only be one swap symbol in the combined program. Although we're talking about C in this particular case, the linkers for C++ and the compilers for C++, historically it depends on the compiler, but historically the way that this has worked is that C++ actually produces symbol names that are simple names like swap here, with some additional suffix information that defines the symbol type. So for example, in C++, I might be able to have two different swap routines, one of which deals with two integers and another one deals with two floats. And they might both have the name swap at the beginning, but then another set of symbols that say this one deals with integers and this one deals with floats. So even in C++, where you can have multiple swap functions, there will be unique symbols in the symbol table. And in fact, C++ uses the same linker that C uses. So what else do linkers do? They do relocation. So as we have code in main.o and sum.o, we need to merge those into a single file. And then each of those files, main.o and sum.o, have different parts to them. So there's the part that holds the program, the text of the program, and then there's the data section. We need to take the text out of the two different sections, combine them into a single section in the resulting program file. We also then need to figure out where in absolute memory the final destinations are. So for example, we'll see that some instructions in the x86 are what are called PC relative addresses. So they go relative to what the current program counter is. Other memory references are absolute addresses. They just need an absolute address in memory for that. The linker, when it relocates things, needs to then, based upon where things are in memory, needs to fix up the call instructions and the load instructions to refer to the right program portions and the right data portion. And then it needs to update all the references to those symbols to reflect their new positions. So let's go into this a bit more detail. So there are relocatable object files, .o files. This, again, as we said, it contains code and data in a form that can be combined with other files. And so in the C world, each .o is produced from exactly one source file, and the .o file can contain multiple functions and multiple pieces of data. There's some other languages where each individual .o file is specific to a given function, and they have often a different linker system. But we're going to focus on what works in C. Then there's an executable object file. So this is often called an a.out file. It contains the code and data in a form that can be copied directly into memory and then executed. So this is basically what an executable file is. When we look at a program, so for example, let's say bin ls, which is the thing that lists program directories, that would be an a.out file or an executable file. There are also shared object files. These are .so files. They're a special type of relocatable object file that can be loaded into memory and then accessed by multiple programs simultaneously. This is increasingly common in pretty much all operating systems. It's heavily used in Windows, where these are called DLLs, or dynamically linked libraries. These are useful in part because they use less memory. So for example, on a running Linux system, you would only have a single copy of libc in memory at a time. The common executable file format is called ELF, which stands for Executable and Linkable Format. It's the standard binary format for object files in the Linux world. Windows has a different format for files, and Mac OS also has a different format as well. Usually operating systems can load one or more different files. So for example, in Windows, with recent extensions to the Windows operating system, you can actually run Linux executables on the Windows operating system, and they can load the ELF files. So, but this is pretty standard across the Unix-like set of applications, Android, things along those lines. So this is then one unified format for each of the relocatable the executable, and the shared libraries. And in the generic term for this is ELF binaries. Just as a side note, there is a debugging format. So for debugging information that is stored in ELF binaries, and that, of course, is the dwarf format. I don't make this up. I just tell it like it is. So the ELF object file has a header that tells you more about the layout of the rest of the file. And then it has a set of segment headers and segments. The segments correspond to different types of data that is going to be organized and stored in memory. So for example, the text segment is code. There's a read-only data segment. So this is data that might be, for example, jump tables from a switch statement. Or statically defined variables that cannot be, or strings that can, for example, not be modified. There's a data section which is used for initialized global variables, and then a BSS section, which stands for block started by symbol or blank storage segment. And this is for global variables that are declared, but you don't explicitly say, you don't have a unique initializers for them. So when these are declared or laid out in memory, they'll be set to 0 by default. And that's just to make it more efficient instead of storing a lot of zeros in the file. There's also a symbol table section. So that has all the symbol table information, the procedure names and the static names and everything else. And then there's a relocation information, relocation for the text and for the data. The relocation information is what's needed to be able to paste together the program code and change its organization in memory, and then fix it up so that it can actually execute. Likewise, the relocation data section for data helps organize like references to other memory and help fix up those references to other global variables that have been done. The debug section then contains debug information, so that's only put in there if you compile with the -G flag. And then there's a section header table that again has more information about the section headers. The linker symbols are broken into global symbols. So global symbols are defined by a given module and that can be referenced by other modules. So these are non-static C functions and non-static global variables. So in C, if I have a single .c file, just to remind you about this, if I have a function foo in that file that I then define and put the body in, that function foo can be referred to by other .c files. And that happens because the symbol foo is put into the symbol table. If I put the word static in front of this, the code will be included. So the code for function foo will be included in this .o file when it's compiled. But the symbol foo will not be in the symbol table, and it will not be, well, it'll be in the symbol table, but it'll be marked as a local symbol. And it will not be able to be accessed by other modules. It will not be a global symbol. External symbols are, so for example, if in that same .o file I call a function bar, but I do not have the reference in that file, that's an external symbol and I need to know where it is. And then there's local symbols, and that would be the equivalent of foo with the static term in front of it. So these are symbols that are defined and referenced exclusively by this single module, and that means things that have the static attribute in front of them. This is different than local variables within a function. Local variables in a function are not managed by the linker. Those are handled at runtime and allocated on the stack, except for one special case that we'll describe a little bit later on, something called static local variables that you shouldn't use. So let's take a look at the symbol resolution process. So here we have a reference to a global symbol array that is defined over there. And here we're defining a global main that isn't referenced in any of the other programs, but it is referenced by a specific library that is the base of everything else in your program, often called CRT0.o, or depending upon the version of the libraries that you're using, possibly something else. And that stands for the C runtime and it's the first bunch of code that is actually going to be executed. And then this has a call to main in it. So it sets up the stuff so that main can be called. Here we're referencing a global sum that is defined over there. The variables like val, which are on the stack, they're going to be stack allocated. The linker doesn't need to deal with those. Now the symbol table information is still in the symbol table because when we're running GDB, we want to be able to refer to the variable val. Likewise, the integer variables I and S, we want those in the debug information, but they're not going to be in part of the linking process. Local symbols, as I mentioned, can be static functions like static foo. One of the other cases that you have static variables in C is this is a way to create a variable that is as if it were a global variable. So in other words, there'll be a single instance of the variable x, but its name will only be known within function f. So this program would actually allocate two different static variables. It's going to allocate space in data for each of the definitions of x, and it's going to create local symbols in the symbol tables with unique names. So, x.1, x.2, x.f, x.g, something. And these symbols, this value of x can only be referred in this function here. In general, you shouldn't use static functions. It has a number, or static data like this. It has a number of complications when you write either reentrant or what are called multi-threaded programs. There are typically other ways to be able to handle the same need if you're looking at static data. And some of it is either just having explicit global data or having what are called thread local storage. So how do linkers resolve duplicate symbol definitions? So this is a distinction between strong and weak symbols. And it depends basically whether something has data or information associated with it. So for example, in P1, we have a strong definition of the variable foo. And that's because we've provided a value for it, 5. We also have a strong definition for the procedure 1 because there's a code body associated with it, even though I didn't write anything there. So P1 is a strong symbol. In P2, we have a weak foo because we didn't actually have a definition or an initializer for it. And P2 is a strong function symbol. The linker has certain rules when linking symbols. Rule number 1, multiple strong symbols are not allowed. So each item can only be defined once, otherwise it's a linker error. So what that would mean is that if I had tried to say int foo equals 10, or even if int foo was equal to 5, it was the same value, the linker would barf on me and not let me do that because I have two different strong symbols. And the reason for preventing this is, again, that if I did have int foo equals 10, which value is supposed to be the initializer? Rule number 2, given a strong symbol and multiple weak symbols, you choose the strong symbol. So the value that defines a definition of either a piece of code or a piece of data is the definition that wins for that symbol. Now note that symbols have no type information associated with them. That's in the debugger, but not in the linking process. Rule number 3, if there are multiple weak symbols, pick one arbitrarily. Now this is going to be, we're going to see that this is dangerous in just a second, but we can override this with the no common flag in GNU C compiler, and in other C compilers, you'll have other flags that basically will alert you to this problem. Let's see what that problem is. So here's some linker puzzles. So in this particular case, we have a weak symbol X and two strong symbols P1. This is going to be a link time error because of the two strong symbols P1. Now we have two strong symbols P1, P2, and two weak definitions of X. We'll pick one arbitrarily. The references to X will refer to the same uninitialized integer, but is that really what you want? So in other words, is what really was wanted in this case that X is supposed to be a static symbol or local to that given .o file? You wouldn't be warned about this at the link time. Unless, of course, you did the no common. Here's another more difficult to understand and possibly much more dangerous situation. So we have two strong P1, P2s. We have one weak Y, and we have two weak X's, except now the X's refer to different types. So in one case, X is a 4-byte integer, and in another case, X is a 4-byte or an 8-byte double. Again, a symbol is a symbol, and it's basically just a location and a size. Well, depending upon what symbol was picked in to resolve this, so for example, if the int x symbol was taken to resolve the double x usage, then the memory locations x and y might be modified anytime that somebody tried to refer to the double value of x. So writes to x in program P2 might overwrite variable y. And how would you ever know? This is again another reason that you might want to express the -f no common in your compilers. Here we have two strong symbols, x and y, and they're strong because we have values defined for them. Over here we have a weak symbol, and in this particular case, this is going to overwrite y, again, just as in the example above. And in this case, it's because we have now forced the symbol to be that int x because it's strong, and the other x is just weak. Here we have a strong symbol and a weak symbol, and references to x will refer to the same initialized variable. So in other words, references to x in P2 will refer to that x. So there's a nightmare scenario. Maybe you have two identical weak structs compiled by different compilers that have different alignment rules. Again, the symbol is just the name, the label of the symbol, and the size, and it'll pick one of them arbitrarily if it's not initialized. So one of the rules to take away is if you don't need to use global variables, don't. If you do need to use global variables, use static if you can. So restrict the use of a global variable to a given module. Or if you are going to have a global variable, at least initialize it so that you know which one is going to be selected. And if you have an external reference to an external global variable, so in other words, if I have in one routine, if I have int x equals 5, if I have other routines that are trying to use that same global x, make it be extern x. Oh, I'd have to put int in there. Use the extern to note that this is a declaration of x, but it's not a definition, so it's not allocating the storage for it. I'm trying to use somebody else's x. The next phase is relocation. So we have, for example, the main.o and sum.o, and then we have some other system code. So this is that C runtime that I was talking about here. All of this is going to be linked together. We're going to have then a single contiguous text segment that can be stored in memory and laid out contiguously, right in memory. And the goal is to have all of this information here be just ready to load into memory and execute. Likewise, we're going to have a data section where we're going to take the initialized sets of data and just stick it into memory. So to be able to do this, we need to be able to relocate code. In other words, we need to combine it and lay it out to be in a specific part of the memory address space. This is done by having relocation entries. So here we have a call to sum and a use of array. This is the use of the array. We're loading the global variable array. When the compiler is actually generating the code for this, it generates a spot for an address, but it doesn't put the final address for the array A in here. It does put in a relocation entry saying that what we're trying to refer to is the global variable array. And when you figure out where that's going to go, please fill in this entry here with the address of A. Likewise, here in the call routine, we're not actually putting in the actual destination address. We just put in zeros here and a relocation entry that says, when you figure out where function sum is, come back and patch this up. Now the difference is that calls are actually what are called PC relative addresses, and we will then need to put in a value that is depends upon the final location of this call instruction itself. When this is relocated, the call instruction here, so when you look at it in GDB, you'll see a call to this location here, the call to sum. But this call is actually a PC relative address, and what it means is go to the end of this instruction plus 1, 2, 3, 4, 5. That's the address of the entry of sum here. So go to the next 5 bytes after the following instruction following this call. So it's a PC relative call. Whereas the use of array here is an absolute address. So the PC relative address, again, is just that the destination address is the address that follows the call plus the offset in there.